I'm excited to walk you through an impactful machine learning system that powers everyday user experiences on modern platforms, the personalized newsfeed. The system is not only central to user engagement and retention, but it also showcases how thoughtful problem framing, data engineering, and model development come together to solve large-scale real-world challenges. We'll explore the system from end to end, starting with the problem definition, clarifying the business and technical requirements, and then diving into how we frame these problems as machine learning tasks. I'll walk you through the data preparation pipeline, model design choices, evaluation metrics, and how these systems are served in production. Let's start with the personalized news feed, a system that must decide, out of millions of potential pieces of content, what's most relevant for you at any given time. The problem is to show friends recent activities on a user's timeline. Here are some good questions to ask in the requirement clarification phase. What's the motivation? What kind of contents are there? What types of engagements are we optimizing for? What are the major reactions available? How fast is the system supposed to work? How many timeline updates do we expect each day? Let's walk through how we can frame personalized newsfeed ranking as a machine learning problem. Our ML objective is to maximize a weighted engagement score. This score reflects how likely a user is to interact positively with a post and is built from both explicit and implicit feedback signals. Implicit feedback includes signals like click-through rate, CTR, did the user click on the post, dwell time, how long did they spend reading or viewing it. Explicit feedback includes likes and reactions, shares or reposts, hides or mark as not relevant, which we count negatively. Each of these can be assigned a weight depending on business goals, for example, promoting healthy engagement or reducing misinformation spread. The input to our ML system is a user, often represented by their demographics and device info, their recent behavior and preferences, e.g., topics clicked on recently, the current context, time, day, location, etc. The output is a ranked list of candidate posts chosen from the universe of posts. The user hasn't seen posts that have been updated with new comments, posts shared by friends or followed pages. We use a pointwise LTR approach to solve this. This means the model learns to predict a relevant score or engagement probability for each user post pair. Each sample is treated independently, and the objective is to minimize the loss between the predicted and actual engagement score. We can model this as a classification task, e.g., will click our 1 or not our 0, or as a regression task if we're predicting something continuous like dwell time. This approach is scalable and easy to train, and it integrates well with deep learning models that use embeddings for both users and posts. This setup gives us flexibility. We can continuously retrain the model as user behavior shifts. We can dynamically adjust how much we value different forms of engagement. It allows us to incorporate rich feature sets, user interests, post metadata, and even embeddings from content like images or text. We begin by collecting 4 core types of data. Users. Basic user profiles including IDs, demographic data, and platform activity patterns. Posts. These are the candidate items we may recommend. Each post has metadata like the author, content type, text, image, video, and timestamps. User post interactions. This includes implicit signals, clicks, dwell time, and explicit signals, likes, comments, shares, hides. These interactions form our labels and help us understand user preferences. Friendship. Social connections are vital for relevance in a feed. A user is much more likely to engage with content from friends or mutuals. Feature engineering. To feed our model useful signals, we extract meaningful features from both users and posts. Post features. Content includes the raw text, topics extracted from NLP models, and content embeddings. Reactions. Counts of likes, shares, and comments help indicate popularity. Hashtags, useful for trend-based relevance. Age, time since posting. We want to balance freshness with engagement potential. User features, demographics, age, location, and gender, if available, help customize relevance. Contextual info, device type, time of day, or recent activity session can influence recommendation decisions. Historical interactions, past clicks, likes, shares, give us direct signals of interest. Mentions and social tags. If a user is mentioned or tagged in a post, this can be a strong engagement cue. User-author affinities. Measures like how often a user engages with a particular author help capture ongoing interests. Engagement rates. User-level stats like average, like, click, comment, share rates give the model a sense of overall activity level and behavior bias. These engineered features are fed into our ranking model. Well-designed features can make a significant difference in model performance, especially when working with limited labels or sparse interaction histories. Let's dive into the model development for our personalized newsfeed. Multitask Deep Neural Network, MTDNN. We model this recommendation task using a multitask deep learning architecture because user engagement comes in many forms: clicks, likes, shares, comments, and more. A single task model would fail to capture the full behavioral spectrum. Shared layer. At the bottom of the architecture, we have a shared embedding and representation layer. This layer takes as input user features, demographics, historical behavior, interests, device, time of day, post features, content embeddings, text, image, hashtags, freshness, engagement stats. These features are combined and passed through dense layers to form a shared user post interaction representation. Task-specific heads. On top of the shared representation, we place separate output heads, each corresponding to a different task. Click prediction, like prediction, share prediction, comment prediction. These tasks are all modeled as binary classification problems, where the label is whether the user performed the action. For passive users, implicit feedback. Not all users engage explicitly. Some users scroll and read but never click like or share. To still capture their preferences, we incorporate implicit signals. Dwell time, how long the user stays on a post. Skip behavior, whether the user scrolls past the post quickly. These are treated as additional tasks. Dwell time is modeled using regression, since it's continuous. Skip is modeled as a binary classification, skipped versus not skipped. This makes our system robust to different user types, active and passive alike. Training data construction. We construct training examples from historical interactions, positive examples, the user engaged, clicked, liked, etc. Negative examples, the user saw but didn't engage. For implicit signals, we generate pseudo-labels using thresholds, e.g., dwell time, twos, are, skip. We must be careful with label imbalance. Most posts aren't clicked or liked. We address this with negative sampling, loss weighting, optional focal loss for rare events, loss function. Each task has its own loss for click, like, share, comment, and skip. Binary cross-entropy loss. For dwell time prediction, regression loss, often mean squared error, MSE, or mean absolute error, MAE. These individual losses are then combined, usually with learned or fixed weights, into a single objective function. This ensures the model learns to balance trade-offs. For example, it doesn't overly optimize for clicks at the expense of shares. This multitask architecture allows the model to share knowledge across related tasks, personalize across different engagement types, handle sparse and noisy behavior, adapt to both active and passive user behavior. This approach helps drive higher engagement and more relevant feed ranking for a diverse user base. In this section, we'll go over how we evaluate the performance of our personalized newsfeed system. The evaluation is split into offline and online metrics. Both are crucial, but serve different roles. Offline metrics, PROC, precision recall area under the curve. This is our key offline metric for evaluating model quality. PROC is particularly useful when dealing with imbalanced data sets, which is common in newsfeed scenarios. Most posts are not clicked or reacted to. It measures how well the model distinguishes between relevant and irrelevant content, focusing more on the positive class than ROC AUC does. A higher PROC means the model is better at pushing relevant content higher in the feed. Offline evaluation allows us to iterate quickly without user involvement, but it's only a proxy. It doesn't capture real-world dynamics like novelty or user satisfaction. Online metrics. Once we deploy the model, we rely on real-time metrics from A/B testing or production monitoring to assess its impact on user behavior. CTR, click-through rate. This tells us what fraction of shown posts are clicked. It's a direct measure of interest and relevance, and one of our most important online metrics. Reaction rate measures how often users engage more deeply by liking, sharing, or commenting on posts. A high reaction rate indicates that the model surfaces emotionally or socially engaging content. Total time spent. This helps us understand whether the content keeps users engaged over longer sessions. It's a strong indicator of content stickiness and is particularly relevant for long-form or immersive content. Satisfaction rate, survey-based. This is gathered through occasional in-app surveys and provides explicit feedback. It captures how users feel about the content they see, which may not be evident in behavioral data alone. A model that increases CTR but decreases satisfaction may be optimizing for short-term clicks at the expense of long-term trust, so this metric is essential to track. We use these metrics in combination to ensure the model improves both immediate interactions and long-term user satisfaction. Let's now walk through how we serve a personalized newsfeed to users in real time, from preparing the data to making ranked predictions on the fly. 1. Data preparation pipeline. First, we need to continuously prepare data that powers our models. This includes online and batch feature computation, such as post freshness, user post interaction rates, and social signals. Label generation, collecting implicit feedback, e.g., clicks, dwell time, and explicit reactions, e.g., likes, shares. Training dataset creation, which blends recent interactions with a balanced sample of skipped and engaged posts. This pipeline is essential for ensuring our models stay fresh and adapt to evolving user preferences and content trends. 2. Prediction pipeline. Once the data is ready and the model is trained, we move into the real-time serving flow. Retrieval service. The first step is to retrieve a broad pool of unseen candidate posts. This is done via fast heuristics or pre-indexed embeddings, focusing on efficiency and recall. The goal is to capture potentially relevant posts from a vast pool based on the user's identity, friends, topic interests, and recent activity. Ranking service. Next, we take each user, post pair, and pass it to our ranking model. The model computes engagement scores using features like users' past behavior, post content type and metadata, contextual signals, e.g., time of day, session depth. This step prioritizes personalization and optimizes for multiple signals: clicks, dwell time, reactions. Re-ranking service. After scoring, we may apply business logic or editorial policies. Enforce diversity, not too many similar posts. Deprioritize low-quality or spammy content. Promote content from new or underrepresented creators. This ensures the final feed balances relevance, variety, and fairness. Performance and latency. The end-to-end pipeline is highly optimized for latency, typically under 100 milliners from query to ranked list. We use caching of features and model predictions, efficient model architectures, async or streaming feature lookups.